Okay, welcome back to Love in the Physics, Mr. Goldthorpe. So we'll move on to our next force called the friction force. And the good news is you have a pretty good idea of how sliding friction works already, especially when it comes to the direction of friction force. Because it turns out, logically, it acts opposite to the motion or opposite to the velocity, and it'll always be parallel to the surface. So for these two examples here, if we have an object that's moving to the right, so the velocity is to the right, then the friction force will go to the left and parallel to the surface. Similarly, if we have an object that's actually sliding down a slope, then friction will act up the slope, opposite to the motion, parallel to the surface. So pretty logical. Now the equation for friction is Ff is equal to mu Fn. And you should know that this is a magnitude only equation. Notice there's no arrows on the top. It's just the magnitudes for each of them. And so it tells us that friction is actually based on a couple of things. One, the normal force, and two, something called the coefficient of friction. Let's talk about each of those and how they relate to friction force. So, based on this formula, if we talk about normal force, if you look at Ff and Fn, you'll notice that Ff is directly proportional to the normal force. And if you remember, normal force is how hard the two surfaces are squeezed together. So the more you squeeze the two surfaces, the greater the friction force. So, if you'll notice again, for this person right here standing on the ground, the first diagram here, this person might experience, let's say, a certain amount of normal force. But understand, if you put a backpack on, there'll be greater normal force, and thereby a greater chance for friction. Or if you push down on the ground, you'll get a greater normal force, and therefore a greater amount of friction. So if you squeeze those two surfaces together, you end up getting a greater amount of friction. So just to illustrate that, to make that crystal clear for you, let's imagine that this friction force happened to be that big. Then the other cases, they can actually have bigger friction forces than the original. Greater the normal force, the greater the friction force. Now the other one is actually based on what we call the coefficient of friction. And similarly, Ff is directly proportional to this thing called mu, the coefficient. Now it's called a coefficient because it has no units whatsoever. It's just a number. And it tells you how rough the two surfaces are kind of against each other. So, for example, if you have a basketball shoe and it's, let's say, on concrete, so we call it like rubber on concrete, those are the two different surfaces, then they actually have a coefficient of about 0.98. And by the way, mu should be less than 1. So this one is really close to 1, which means an extremely high value for the coefficient. That's because the two surfaces are extremely rough. And so you get extremely good traction when you put a basketball shoe on concrete. But if you take that same basketball shoe and you decide to put it on ice, well, it's a whole different picture now. Even though it's the same shoe, now the coefficient is 0.005. So it's really small, which means you get very little friction and you end up slipping around and possibly hurting yourself. So you don't wear basketball shoes on a slick ice surface. That's not the best choice. Good? So the coefficient is how rough the two surfaces are with each other. So if you bring all this together, if you want to get the greatest amount of normal force possible, all you need to have is the greatest normal force. So make sure you squeeze the surfaces as hard as you can together, and then make sure that both surfaces are extremely rough with each other. And then you'll get the greatest normal friction force possible. All right, and that leads us to our example. Okay, so we have an object that's being pulled east we're told the coefficient of friction, and we're going to try to figure out what the acceleration happens to be. Okay. Let's draw the diagram for this one. And what you're going to find out is when you're dealing with friction, you have to draw both vertical and horizontal forces. So let's imagine this happens to be the object. And I'll just draw the ground as a dotted line. Remember, just draw the object. And let's say it's being pulled east, and let's say east is to the right with a 400 Newton force. So here's the applied force of 400 newtons, causing it to move to the right. So it's moving east. So separate from the diagram, it's moving towards the east. So that's the direction of the velocity. So what is the direction of the friction force? Well, friction goes opposite to the velocity. There's our FF. Now with a different color, I'm going to do the vertical forces. So we know that vertically, this box will experience a force of gravity. There's your Fg equal to mg. But you realize that gravity is going to push it into the ground. So what's the ground going to do? It will push back up. And that will be the normal force. So this is a complete force diagram, both vertical and horizontal. Now, let me now show you why we need to do that. Let's start with vertical. Which we're going to call the y. So let me just put in a quick reference system here. So the question is, vertically speaking, do you guys know which law would that actually be? Now, this object that's going across the surface, you have to realize it's not accelerating off the surface, not flying into the air, and it's not accelerating into the surface, not digging into the ground. So vertically speaking, there's no acceleration. So that would be Newton's first law. So it's Newton's first law vertically, which means if you add up all the forces vertically, you will get 0. And you can see that Fn is positive, Fg is negative, equal to 0. And so therefore it stands to reason Fn will be equal to Fg. They're equal in magnitude, basically equal but opposite, so they cancel each other out. So that's going to be equal to mg, and the mass here is 37 times 9.81. And so now we go with the normal force. It's about 362.97. Now, why do we need that? Well, it turns out this is going to help us find the friction force. So I'll do this as a kind of a separate calculation. Let's now find FF. See, FF on your formula sheet is equal to mu Fn. And we're told what the coefficient of friction is. The coefficient of friction is 0.68. And notice there's no units. That's called mu. So mu, again, is 0.68 times 362.97. So that's about 246.82. And I can transfer that to the diagram here. So that's going to be 246.82 newtons. Okay, that's kind of our second step. I'm just going to transfer this diagram down for the last step. Okay, so now we're ready to take this thing on horizontally. And we're looking for the acceleration. In fact, take a look at this diagram. Which way would it accelerate? Can you see that the force to the right is bigger than the force to the left? So that means that this thing will accelerate to the right. So, because there's acceleration, that'll be Newton's second law. So now we know this is going to be F net equal to ma horizontally. So, horizontally, you see that F is going to the right, so that's going to be positive. FF is resisting it. It's going to the left. It's negative, equal to ma. So just get A by itself, F minus FF over m. And that's going to be, in this case, 400 minus 246.82 divided by the mass of this object, which was, again, 37. Just enough space to finish that. And sig digs, looks like we have two significant digits for our answer here, so it's going to be 4.1 meters per second squared east. Okay, so let's just review. So when you're doing a friction-based question, you're going to want to draw both vertical and horizontal forces, and you analyze them separately with Newton's laws. In this case, vertically there was no acceleration, so it's first law, but horizontally there was acceleration, so it's second law. Good. This is this is great practice for you guys, because after you have the mid-test, or in the second part of this unit, we'll be dealing with two-dimensional force diagram situations, and this will give you a good idea how we're going to take those things on. So, give the homework a try, and I'll see you in the next part of this lesson.